So if we look at the, we already saw the derivation of the alpha t, so now let's look at the error. The error term, as I was saying, in that Taylor series, starts off being negative 1/2 the sum of the RIH squared. That's the first term of the error. In the logarithm, the next error term would be an r cubed, but since r is expected to be small, let's just informally ignore the higher order terms and say, well, since r is going to generally be small when h gets small, that the r cubed will be even smaller than the r squared. Let's just focus on the r squared and be informal. Well, what do we know about r? We know that we can calculate the expected value of this error term because we know that r, each one of these, is, as I said a minute ago, normally distributed with a mean of alpha h and a variance of sigma squared h. So, in fact, if I wanted to look at this variance, the variance of the expected value of this error term looks like -1/2 the summation of variances. It's -1/2 the summation of variances, the RIHs. Now, the variance of the RIHs, well, it's not quite that. It'll be -1/2, and we can write the expected value as the variance plus the mean squared. In other words, we are using the formula that the variance is equal to the second moment minus the mean squared. So here what I'm looking for is the expected value of the error, which is the second moment, and I'm saying that that's equal to the variance, and then I have a mean squared term. So because I'm going to let n go to infinity, I'm going to ignore that. And if I now look at this variance term, I have a sum of variances. Each one is a variance of sigma squared h, so I have a summation of sigma squared h, so I have n of them, recall. And that's -1/2 summation of sigma squared nh, nh is t, and you see the adjustment of sigma squared t. Admittedly, there's a whole lot of hand waving that needs to take place here, but what we've done, there's a whole lot of hand waving that I did in this derivation, and more formality needs to take place to justify this. But I think it's relatively easy to see that the error term has an average value of around -1/2 sigma squared t, because this extra term we can throw away. And so what else are we ignoring? Well, we have sums of r cubed, sums of r fourths, and we ultimately we can show that those error terms go to 0 just like this one does. So all we've now shown is that the expected value of the error, the average error term, is the adjustment we're looking for. It's the adjustment to the mean, the alpha t mean, and we adjust it by -1/2 sigma squared t. Well, this is just the expected error, the average error. The question then becomes, how variable is the error? And here's where the mathematics gets a little more formal, and I won't pursue it. But it turns out that if I look at the variance of the error, the variance of the error goes to 0. So we have a derivation that's reasonably concise and reasonably formal, that the average error is the adjustment that one sees in that earlier formula for geometric Brownian motion. But the outstanding question is, gee, that error looks like a random variable. So it's not okay to just make believe it's this constant. However, the formality that needs to be pursued is, what is the variability of this error? And it turns out that as n gets big, which is the same as saying when h gets small, that the variance of this error term goes to 0. In other words, the error term not only has a mean of minus a half sigma squared t, but in fact it becomes less and less variable and ultimately converges to this value in total.